Episode 15, Design, Electrical. The information that I provide here is simply my research on electricity and electrical codes. I'm sure that there are oversights and errors, but it will give a general overview of what electricity is, how it comes into your home, and how to minimize some of the errors that you might make. It will, at the least, give you a little knowledge so that when you watch someone wire your home, you will have some idea of what they are doing. Minnesota gives a great 7-page guide that highlights relevant code. The link is in the comments. Some entries in the guide. All wiring, including underground cable and conduit, must be inspected at the rough-in stage before it is concealed by insulation, sheetrock, backfill, or other materials. Except for the final connection to switches, receptacles, and lighting fixtures, all equipment grounding wires in boxes must be spliced and pigtailed for the rough-in inspection. It specifies which outlets must be tamper-resistant. It gives AFCI, GFCI guidance. More on these later. It specifies minimum circuits and amperage. 20 amp dedicated circuits, 2 for the kitchen receptacles, 1 for the laundry receptacle, 1 for the bathroom receptacles, 1 for the garage receptacles. There must also be 1 individual branch circuit for central heating equipment, i.e. your furnace. Outlets at wet locations must have a WR extra duty cover. Here's a table for copper wire size based on breaker amperage. 15 amp breakers require 14 gauge wire, 20 amp breaker, 12 gauge wire, 30 amp breaker, 10 gauge wire, 40 amp breaker, 8 gauge wire, and 50 amp breaker, 6 gauge wire. Habitable rooms must have a receptacle outlet not more than 6 feet horizontally from any point along the floor line. At least 1 receptacle outlet must be installed in each wall space 2 feet or more in width. This means 12-foot maximum between outlets and an outlet within 6 feet of a door. Kitchen countertops, no spot more than 2 feet horizontally from an outlet. No outlet within 3 feet horizontally or 8 feet vertically from a tub or shower, unless for a bidet or electronic toilet. Fan-rated ceiling boxes are required in habitable rooms where a fan might be placed. Secure all in-wall wires with a maximum of 4.5 feet between staples and within 12 inches of the box. Metal boxes must be grounded. If you have multiple circuits coming into a single box, all of the grounds need to be tied together. All punched-out openings in boxes must be used. If a plastic punch-out has been opened and is not used, the box must be replaced. Terminal boxes require a 3-foot clear space in front, starting at the floor to 6.5 feet high. No piping, ducting, or apparatus is allowed in this area. And in the 2023 code, external disconnect for all power is required. Overview of electricity to your home. The United States electrical system is primarily a 120-volt alternating current, AC, system. The electricity is generated in very tightly controlled process, running 2 sine waves of energy at 60 cycles per second each, also referred to as 60 hertz. The peak voltage of the sine wave, either the blue or black wave in the diagram, is about 170 volts. This means at times the voltage coming out of your outlet is plus 170 volts, sometimes it is 0, and sometimes it is negative 170 volts. The average energy of this wave can be approximated by using the root mean square, RMS, of the sine waves. The RMS value of this sine wave, also known as the effective value, is 120 volts. This is the same amount of power that a 120-volt direct current, DC, source would provide. But, say you, we have some appliances in our house that are 120 volt and others that are 240 volt. If all we get into the house is 120 volts, how can we have a 240 volt appliance? The answer is that you get 2 different power wires into your house. They are each 120 volt, but the sine waves on them are perfectly out of phase. So when one of the wires is producing plus 120 volts, the other is providing minus 120 volts. The difference between these voltages gives you the 240 volts. So, from the street, you have 2 wires, a plus 120 volt and a minus 120 volt wire. These are brought into your circuit breaker box, also known as a load center. Load centers come in 2 types. Some have plug-on neutral, PON, and some do not. The load center depicted here is a plug-on neutral load center. Plug-on neutral means that the circuit breakers have 2 electrical connections in each breaker, a power connector, and a neutral connector. Connections in your plug-on neutral load center. The power bars. Each load center has two power bars, one for the plus phase of power, depicted in yellow, one for the negative phase of power, depicted in purple. The hot load connector on the circuit breaker attaches to the neutral bar. The black load wires normally will connect through to the power bars. The neutral bars. Each plug-on neutral load center has two neutral bars. The neutral connector on the circuit breaker attaches to the neutral bar. These neutral bars are attached to the ground bars at the top of the load center. The white neutral wires normally will connect through to the neutral bars. The ground bars. Most load centers will have two ground bars, depicted in green. The ground bars are grounded to the house ground, copper rod, rebar, etc. The bare copper wires will connect to the ground bar. Blades. The power bars each have blades that the end of the circuit breaker clips into. Remember, these bars are 120 volts each. Circuit breakers across from each other plug into the same blade. One uses the left half, the other the right. These opposite circuit breakers are powered by the same phase of power. In the drawing, the top two circuit breakers would be on the yellow power bar. The next set of two circuit breakers would be on the purple power bar. When we want 240 volts, we use a breaker that is twice as wide, and it plugs into both a yellow blade and a purple blade. That way it can have both phases of power at the same time, resulting in 240 volts. Circuit breaker types. Normal, not plug-on neutral. The circuit breaker hooks into the load center with a non-metallic, non-conducting hook. The circuit breaker has only one metal connector on its back. This blade connector is for the power connection. This circuit breaker has only one screw to attach a wire to the breaker. This is for the black wire to your outlets, lights, etc. You can put a ground fault interrupt and or an arc fault circuit breaker into a non-plug-on neutral load center. Again, there's only one metal connector on the back of the circuit breaker. This is for the power connection. The circuit breaker hooks into the load center with a non-metallic, non-conducting hook. There is a white pigtail wire that will attach to the load center neutral or load center ground. This circuit breaker has two screws for wire attachment, load power for the black wire and neutral for the white wire. Here is a ground fault interrupt and or arc fault circuit breaker for a plug-on neutral load center. This circuit breaker has two metal connectors on the back. One is for the power connection, the other is for the neutral bar connection. The circuit breaker hooks into the load center with a metallic conducting hook. Two screws to attach wires to the breaker, load power for the black wire and neutral for the white wire. My primary terminal box is a plug-on neutral PON load center. This is the type to have. Make sure you buy plug-on neutral breakers. As we discussed, plug-on neutral means that there's a neutral bar that each circuit breaker plugs into the full length of each side of the box. In non-plug-on neutral boxes, breakers only plugged into the hot line. Plug-on neutral breakers plug into both the hot line and the neutral. This load center is an Eaton type BR200, 40 amp, 40 circuit, 80 space, indoor main breaker, plug-on neutral load center. The model number is BRP 40 Bravo 200V25. It has a 200 amp main breaker. The power from the street normally enters your load center through a 200 amp breaker. You can see the two large wires, one of each phase, entering from the right. My load center had only 40 slots for breakers. This was not enough. I added a secondary circuit breaker box with 12 more slots. It is a BR 125 amp, 24 circuit, 12 space main lug indoor plug-on neutral load center. Model number BRP 12L125V24. This panel is rated to 125 amps. I elected to use a 100 amp breaker in the main panel. To connect this subpanel to the main, I used 2-gauge aluminum wire for the two power feeds and the neutral, 4-gauge aluminum wire for the ground. Per code, the neutral and ground bars are separated in the subpanel. The subpanel neutral is only tied to the main panel neutral. Why did I need so many circuit breaker slots? Well, by code, the kitchen alone needed 7 circuit breakers. 4 appliances required dedicated breakers: the microwave, fridge, dishwasher, and stove. and my outlets required 3 breakers, and you can wire 2 outlets max per breaker. The house requires the electrical system to be grounded. This means actually in the ground. I elected to use a system known as an Ufer ground, which is an electrical earth grounding method. It is often used for structures with concrete foundations. It was developed by Herbert G. Ufer in 1942, and in 1968 was first permitted in the National Electrical Code. In 1978, the code was modified to allow for half-inch rebar to be used as the grounding electrode. The code refers to Ufer grounds as concrete encased electrode. The code requires that the concrete encased electrode must be encased by at least 2 inches of concrete and located within a portion of concrete foundation or footing that is in direct contact with the earth. You must route the grounding electrode conductor into the footing and connect it to 1 or more bare or zinc galvanized or other electrically conductive coated steel reinforcing bars or rods of not less than ½ inch in diameter, installed in one continuous 20-foot length, or if in multiple pieces connected together by the usual steel wires, exothermic welding, or other effective means to create a 20-foot or greater length. And the URL is listed below. Other electrical notes. National Electrical Code has requirements for arc fault circuit interrupter, AFCI, and ground fault circuit interrupter, GFCI, line protection. Almost all circuits will require either AFCI or GFCI, and many require both. This can be most easily accomplished by using dual-purpose combo AFCI/GFCI circuit breakers. AFCI breakers are required on 15 or 20 amp 120 volt circuits. GFCI breakers are required on 125 volt to 250 volt receptacles supplied by single phase branch circuits rated 150 volts or less to the ground. Also, GFCI protected receptacles are required in bathrooms, garages, crawl spaces, basements, laundry rooms, and areas where a water source is present. The only circuits that don't need AFCI or GFCI protection are dedicated light or smoke alarm circuits. In my build, the only circuit we have like this is the smoke alarm circuit. Smoke alarms are not permitted to be supplied by a branch circuit protected by a combo, ground, or arc fault circuit interrupter, GFCI, AFCI, because during a fire situation, the interrupter may trip and potentially disable the smoke alarm. The GFCI, AFCI breakers help in preventing electrocution and your house burning down. However, any current in the neutral wire will trip these breakers. We had a large coronal mass ejection, CME sunspot, the activity that causes the northern lights. When this solar storm hit the earth, we had 6 circuit breakers trip. If you don't happen to be home and any of these circuits are for a critical function, such as your boiler pump or your freezer, you are toast. Be aware that these breakers are sensitive. These new circuit breakers cost up to 10 times more than the standard circuit breakers, $40 versus $4. Code requirements like these have driven the price of new homes way up. I have 60 circuit breakers. That's $2,400 versus the $240 I would have spent prior to the code update. Some unscrupulous home builders have traveling circuit breakers. They put in these code-required expensive breakers to get through inspection and then remove them, replace them with non-protecting breakers, and then take them to the next job site. This is bad on many levels: theft from the homeowner, code violation, etc. URLs are listed below for this information. There is also a requirement that some circuit breakers have lockout capabilities. The lockout is a small flange that attaches to your normal circuit breaker. This requirement primarily applies to your hardwire dishwasher circuit. The next states, the branch circuit overcurrent device shall be permitted to serve as the disconnecting means where the switch or circuit breaker is within sight from the appliance or is lockable in accordance with 110.25. Within sight from the appliance does not only mean that while flipping the switch the electrician can see the appliance, it also means that while servicing the appliance, the switch can be seen by the electrician and it is within 50 feet. If it doesn't meet the within sight requirement, the circuit breaker is required to be lockable. There are also requirements for an external outlet for air conditioners. Under the GFCI requirements given earlier, these circuits require protection. Some discussion on wire sizing. Code requires A 15 amp circuit cannot have wire smaller than 14 gauge, and a 20 amp circuit cannot have wire smaller than 12 gauge. This is really a function, though, of length of run. If your run length is greater than 50 feet, you need to step up your wire gauge to the next size. There is also a requirement that an outlet be provided near your passive radon venting system. You must install an electrical junction box outlet in the attic for use with a vent fan should, after testing for radon, a more robust system be needed. Other items to consider. Place top of light switches 48 inches from your floor. This allows for easier install of drywall. Place top of vanity outlets and switches 46 inches from the floor. Cleat to move boxes away from door frames so that you can place trim around the door. A cleat is just a piece of 2x4 or 2x6 to move your switch laterally. Outlets. Rule of thumb, 10 boxes max per circuit in rooms. Bathroom outlets must be dedicated 20 amp, 2 boxes max per circuit. If you have a single outlet on a 20 amp circuit breaker, it must be a 20 amp outlet, not a 15 amp outlet. I have 4 outlets like this: microwave, fridge, washing machine, and lift station. These are all installed as 20 amp outlets. Outside outlets. Damp area. Weatherproof cover when not used. Wet area. Weatherproof cover when in use. Bathroom lights and fans do not need dedicated circuits. They can tie into nearby circuits. When you run the wire for the oversing bathroom lights, you don't yet know where those lights will be. Cap the wires and leave loops in the wall so that later you can fish the wire to its desired position. More considerations? Internet and connectivity. I also wired the house and garage with Cat 6 wire to every room. This allows for several things. Hardwired distant connection for items like the garage security cameras. Hardwired distant connections for Wi-Fi mesh. Doorbell wires and power source. If you plan on having a wired doorbell, you need to have a transformer somewhere and a power signal wire that goes between your transformer and the doorbell location. I planned on placing the transformer in the basement utility room. Security considerations. You may want security cameras and floodlights scattered around at different places on your house and garage. These may need wired power and perhaps a wired LAN. Some use Wi-Fi for the connectivity, but this can be jammed. It's critical to include in your early design the pre-placement of the wires, power and signals, to the areas where you might put these devices. I used Ring products at other locations, so I decided to stay with the same. I placed one floodlight Cam Pro wired on the garage. It's wired to plug-in, model B08FCWRXQR, white, and you can get those at Lowe's. I put 2 Spotlight Cam Pros wired above the deck facing the lake. They were $250 on Amazon. They're the Bravo 09 DRC LHQT in black. And lastly, I put a Ring video doorbell on the house. One drawback of this in the Great White North is that even when wired to a transformer, the battery becomes non-functional when the temperature gets down around 0. At that point, the unit fails until it warms up again. There are some little kits that put a very small warming patch between the device and the house. I'll probably build one of these so that I can have a functional doorbell camera all the time, even in the sub-zero cold.